Hi, welcome to another PlayBASIC live video. Today I want to actually look at something that came up in another discussion, and I thought maybe it warrants a bit of a go over here as well. It's actually to do with division. So if we have an expression like this, we have result, we have a value like a literal value like 5, for example. Divide 5 by 2, and we'll print the result out, our result variable out, and we'll have a sync and a wait key so it'll stop. And you might notice, hopefully you can see the result there is 2, it's integer 2. Now, you might be wondering, some of you might be wondering, why wasn't the result 2.5? Now, PlayBASIC and actually most kind of traditional basics have adopted a set of rules over the time that are unlike C, for example, where when we do a divide, a compiler looks at the value on the left and the right hand side of the operator, and if they're both integer, it will do an integer based division and return an integer result, as opposed to if either side is a floating point value. So if I have, let's say, 5.0, when the compiler sees this, it will actually do a floating point division, so we'll get 2.5 as a result, but that float is then being written back to a integer, so we won't actually see the result coming through. As you can see, we get 2. What's happening is we're doing our division the way we expected. We're using the FPU in this case to do it, and writing it back to an integer. So if we made this a float, made the second one there a float as well, we would see 2.5. If I go back and take away that, so now we have integer 5 divided by integer 2, which will be integer 2. It won't be 2.5, and that integer 2 is then transferred from the integer pile into the float value of result. So we'll get 2.0. I know I'm rushing a little bit, and the reason why this is a kind of an issue really is that inside your computer, inside your CPU is actually 2 chips inside the one box. In fact, these days they're more like about half a dozen chips in one side box. But so we have an integer side of the chip which does all, there's a integer add operation, subtraction, multiplication, division, etc. You can do comparisons, all that kind of stuff, bit shifting, manipulation, ANDing, masking, which is all fantastic. And then we have a second part of the chip called the FPU, and that's to do with floating point operations. So it can do things like simple stuff like addition, subtraction, floating point values, multiplications of floating points, that kind of stuff. But it also has other stuff like cosine and sine operations and square roots even, and a few other bits and pieces in there as well. Traditionally, what we used to have is that we would actually have in our sort of 486 generation computers, so we're talking about mid-90s here or early 90s, is your computer would just have a 486 chip which is integer only. It had no floating point capabilities at all in hardware. The sort of the Pentium generation, the FPU was integrated into the chip as well. So this has actually had a kind of a byproduct on languages. So we actually have 2 different types of division, 2 different types of addition. And in a language like PlayBASIC, we kind of have to let people get away with kind of stuff In some languages, if you went and did 5 or floating point 5 divided by integer 2, it might throw an error because it's expecting both sides of the operator to be the same type. So you might, in some other language, you might actually have to put a float around that, for example, which is kind of silly. You could just put the dot after it, really. Am I making any sense with that? Alright, there's actually an article on the forum here somewhere. I should have looked this up before. I think it's in the FAQs. Very old conversation, quite a common problem people run into. You know, if you jump around and look through a lot of different languages, what you tend to find is that some languages only do floating point operations. So anytime you have a division or addition or multiplication or whatever, they are all done as floating point, which means that our example would have worked originally. We would have got what we kind of expected, 2.5. But in those languages, what you tend to get though is variables are variants. They can be integer, float, string, all kinds of stuff. They can kind of morph into whatever you want. In BASIC, we have very strict rule, or in PlayBASIC, I should say, we have very classic rules, I guess you'd call them, strict maybe, where we have 3 different variable types: integers, floating point. They're the 2 numeric types, and we have a text form which is called the string. Anyway, getting back to our forum here, I think it's in variables and math questions, but we'll hopefully find it there. These FAQs are on the main site too, by the way, so on the playbasic.com site. Oh, there you go. I think this actually came in as a question one day, and I made it into an FAQ article. But this is kind of the same kind of stuff. So here we're saying, in calculations, I noticed that PB does not recognize numbers like answer equals 2.45 plus 7.28. Is this normal, or are we doing something wrong? Well, let's take a look at that expression. So if we have this bit of code, I'll just grab it from there and put it in PlayBASIC. Okay, get rid of that. Try and get. Okay, so we're going to print out answer now. What are we doing here? As PB is coming down, it sees the variable, the implicit variable usage, so it creates an integer variable called answer. Scans across the row and goes, okay, you want to assign something to this variable. We see a literal floating point value of 2.45. We see the addition operator and a literal value of 7.28. So the compiler sees the addition and goes, okay, we want to add these 2 numbers together and then write them out, write the floating point result, because notice how, the addition here will use floating point addition because the left side is a float and the right side is a float. Now, even if only one side was a float, it would still use floating point addition, which means we can have fractional numbers. So it would do the floating point addition, and then once that's done, it has to write this result back into an integer variable. So any leftovers, any part of that isn't the whole number, will get truncated away. Let's have a bit of a go. So we've got our result is 9. Right, so we've got 2.45 here. So if you're expecting 9 point, what would it be? 9.7-ish kind of thing. To get that result, answer would have to be a floating point variable, and to print out that variable we need to add the hash down there as well. So let's run it. That's much better. So we're getting our expected behavior. And this can trip people up. Right. So in some languages, for example, you wouldn't be allowed to do this. It would actually give you a warning and say, oh, yeah, you've got floating point data over here after this addition, but you're writing this back to an integer, and there's going to be some loss of precision in that computation. Do you want to do that, or is it okay? You know, in PB, it's kind of one of the rules we decided early on. In most basics, you find the same basic rules. Is it doesn't give you implicit. It doesn't give you scary warnings all the time, I should say. Right. So the rule is kind of demonstrate the rest of this. It's on the forum here. Check out this particular article if you're concerned. But this is the table I wanted to pick up. Okay, so how come when I do a division between two variables or values, the result is integer? Which is what this whole little chat's about today. So the answer is during math operations like addition, subtraction, multiplication, division, PlayBASIC automatically casts. In other words, it picks what data type the result is going to be, and it makes that choice given the types of the two input values or variables from this following table. So in this case here we're talking about division, but this is also true for addition, subtraction, multiplication. So when the data on both sides of the operator is integer, we produce an integer operation that returns an integer result. So if we have 5 divided by 2 again, we will get that will be solved by the integer part of your CPU, and the result is written back out as an integer variable. Now that's not true when either side is a float. So if we have an integer divided by a float, this will be done by the FPU part of your CPU, the floating point unit, and it returns a floating point result because we're using the FPU. So, and this is the same no matter if the right side is a float, we're using the FPU. If only the left side is a float, we're using the FPU, and if both sides are floats, we're using the FPU. I hope that makes a bit of sense. So, if you find yourself in a situation where you want to do a floating point division, let's say you have, I don't know, we'll make a few other values. We'll have value 1 divided by value 2. Up here, of course, the way PV works is as it comes down, we'll see these as implicit variable declarations, and it assumes that's integer by default. So we'll go 10. Value 2 will be 3. Let's say. Okay. Fancy, very fancy piece of code, isn't it? Let's run it. So value 1, the variable value 1 is going to be assigned 10, variable value 2 is assigned 3, and they are both integer variables. So when PV phrases this line here out, it creates this result variable, looks at this expression and goes, okay, we've got two variables in here and an operator, looks at this variable here and goes, oh, what type are you? Goes, okay, you're integer. So, and this one here is integer. It's going to pick the integer division operation. So this will be solved as an integer divide. Am I crushing a dead horse there or not? Or not? Let's say we want to make a result a floating point, like we have we did earlier. We run this again, and we get 3.0, but we really desperately want to get our. So all we need to do is we need to cast one of these sides using the float. So what this does is the float operation here takes this integer variable and creates pretty much a temp version of that on the FPU as a floating point. And since this is a floating point, our division operator goes, okay, one of our values is now a float, so we're going to use the floating point division on the FPU, and we'll get the result we expect. We couldn't do something like this, which I've seen a few people do. They tried to recast the result. So what this here would do is it would, because this part here of the expression is evaluated first due to the order operations. So PBASIC would see this expression starting from over here. It looks ahead and goes, oh, okay, we've got a pair of brackets here. It goes, what's inside the brackets? Solves this stuff here first. So it would work out that we've got an integer divide and an integer result from that division, and then we're converting that result to a float and then assigning that across to this result here. So we will get the wrong answer. We'll just get 3. And just to prove it doesn't matter which side we recast as float. If we recast this integer here on the right hand side, we get 3.3 recursive. The FPU has a limit to its precision, by the way, so you can't. I think people tend to think that the FPU is infallible, but really its precision is not that fantastic, and that's not a PV thing. That's how your processor works. 32-bit floating point it's good enough for everyday use in games, but you can find yourself with some loss issues when you start doing operations on big numbers or even really small numbers for that matter. Alright, so hopefully that gives you a bit of insight there. A bit of a reminder about that. Maybe you've okay, the next question here is how precise are floating point values? Well, if you go and check out the link here, you'll discover, you'll be horrified at how inaccurate they actually can be. Oh, I've got some, yeah, that's probably worth noting too, is you can get some rounding errors from certain operations. Random actually is one of these ones that people sort of think works one way, but actually doesn't work that way internally. I won't go into that today. And the rounding can skew results here or there. So if you do find you're getting some kind of weird rounding here or there when doing floating point operations, you want to move those back into integers, then my advice is to force these to be int with the int function. Okay. Hopefully that gives you a bit more insight into that topic. It's a kind of a pretty boring topic, and but it's necessary to help people understand what's going on sometimes. I guess in the future we could have a warning system for when you do stuff like this. Like this line here is now, we have an integer variable declared, but we're declaring it we're assigning it a floating point value. Some people would prefer that those things did trip errors at runtime, and we can do this with variables. We just haven't added. Like if I have explicit, I turn this on, for example, then this won't compile anymore. Nope, because this variable here is not declared inside the global scope. You can just get away and just put local in front of them, which will work. And they are actually they're you mightn't realise it, but how programs work is that the main it's just a giant function. So these are actually local to that scope. And there you go, back to working. The explicit functionality too is it works unlike other languages where if you turn it on, it's on for everything. When it's turned on here and turned off here, it only affects the lines between it. So you can actually share libraries with other people, and you can turn, if they use explicit mode on and you don't like that, you can turn it off and that sort of thing, which can be a bit frustrating for some. Just to demonstrate that, bit of a secondary bit of chestnut there. Oh, old chestnut. All right, thanks for watching, and go out there and mess around with some code and have a bit of fun. Thanks again, and I'll catch you later. Bye.